thank you everyone for being here this morning. And the fact that you are here probably means you care a little bit about the planet Uranus, or you care about free coffee. But I did want to motivate a little bit why we are here and why we're focused on Uranus. And so I think most of you know there are three types of planets in our solar system. There are ones that are basically 100% rock. We live on one of them. There are a couple, Jupiter and Saturn, that are basically 100% gas. Not quite, but they're mostly gas. And there's Uranus and Neptune that we call ice giants. And we're actually not entirely sure what they're made of. They have a density intermediate to rock and gas, but this mystery of not being sure of exactly what they're made of, as humans, makes us interested. You know, anything we don't understand, right, is of interest. So these so-called ice giants, which may be rock giants, we might hear about that later, are a mystery to us. Now, they're of interest not just because they're an oddity in our solar system, however, because they're actually the majority of the planets we know about today. When you look at the thousands of exoplanets we've discovered, the majority of them seem to be more like Uranus and Neptune than any of the other planets. So Uranus is of interest not only because it's mysterious to us, but it's obviously a very important planet to understand, since the majority of the planets that we've discovered are like Uranus and Neptune. Now, for these reasons, or that's one of the reasons, the recent Planetary Science and Astrobiology Decadal Survey has recommended to NASA that a mission to Uranus be a priority for the next decade. So that's another reason to care about Uranus, that we're hoping to be starting soon, relatively soon, in geologic term, a mission to the planet. And when that mission goes to Uranus, there's a lot to do. Every component of the Uranian system has something fundamental about it that we do not understand. So it's a fascinating place to go. But one of the, in my opinion, most important things this mission will do is tell us about the interior structure of Uranus. And that is important because it provides our best clues to understand how the planet formed, how it evolved, and actually how the whole solar system formed and evolved. And understanding our own solar system is what we use to help us understand all the forming planetary systems around other stars. So that is the real motivation for wanting to focus on the interior structure of Uranus and Neptune, because it is one of the keys to understanding more broadly formation and evolution of planetary systems everywhere. And I want to keep an eye on the time. Might give the speakers a little extra time. I'd like to introduce our first speaker, Jonathan Lunine, who is probably very familiar with this room, being a Caltech graduate. Jonathan is the David C. Duncan Professor in Physics in the Physical Sciences, also the chair of the Astronomy Department at Cornell. He has like 40 years of experience looking at everything in the solar system, basically, and currently another area of interest is habitability in the solar system. Actually, I think it's true of all of our speakers. Jonathan has made his career both doing the theoretical work and being involved in space missions. And because he didn't have enough to do with his own research and being chair of a department, he also chaired the Giant Planets panel of the recent Decadal Survey. So this is a topic he obviously knows a lot about. So with that, I will welcome Jonathan to tell us about the reservoirs and processes involved in giant planet formation.
What I am tasked to do is to tell you about the types of materials that were present at the time the giant planets formed, what processes occurred that affected them and brought them together, and what chemical and other markers might exist today to identify those reservoirs and the processes involved. So the last of these is going to be easy, high-resolution interior data for Uranus, gravity data, an atmospheric probe, and so forth, but I hope to motivate a little bit some of the reasons for that. Ravid Haled and Krista Soderlund will speak specifically about the processes by which Uranus formed and the details of what we know of the interior of Uranus. And then Marzia Parisi will talk about the radio science and how to get gravity data. So Mark already motivated this a little bit. I want to emphasize that Uranus and Neptune, as far as is understood, really are different from Jupiter and Saturn. Jupiter and Saturn contain most of the mass in the solar system, and Jupiter's 318 Earth masses is almost entirely, with the exception of a few tens of Earth masses, almost entirely hydrogen and helium. The same is true for Saturn. But if you look at Uranus and Neptune, they're very, very different. So the density of Uranus is just about the density of Jupiter, 1.3 grams per cubic centimeter. Water is 1. It's cut off on the slide. But as far as is understood by trying to fit the density, the size, hydrostatic equilibrium, imposing mass conservation, etc., if you do a simple model of Uranus or Neptune, the amount of hydrogen and helium is much less than the amount of everything else, whatever that everything else is. It's 1 Earth mass of hydrogen and helium, and then 13.5 Earth masses of something else. So the question then is, why did that happen? I'm not going to address that question. That's in the next talk. So I want to talk instead about what kinds of materials were available in the solar system during the time that the planets formed. The solar system, as with other planetary systems, as far as is understood, formed from the collapse of a molecular cloud core, a piece of a molecular cloud, within a cluster of some large number of other stars. The angular momentum associated with that clump of material formed a disk rather than a spherical shape of gas and other things. And there was lots of chemistry that went on. I'll talk only a little bit about that. The kind of chemistry that we're talking about, astrochemistry, forms the basis of, it could be an entire course for an entire quarter or a semester. The outer solar system was a mixture of gas and grains with varying degrees of processing. Some of that material that was in the region where the giant planets formed might have been relatively unaltered interstellar material that just came in late, or it could be material that was completely reprocessed chemically through this protoplanetary disk. And while I'm going to show you data that suggests that comets may be the most pristine bodies that can be studied in the solar system, that is, their composition is closest to, at least from an elemental point of view, the composition of the sun, they're not in their original formation location, and they're not necessarily representative of the vast majority of material, solid material, that was present in the early solar system, because most of that material is gone. It's either in the giant planets or it's been scattered away to where we cannot access it. So let me then motivate these points. So this is a diagram from a paper by Evine van Dishoek et al., including myself in Protostars and Planet 6. It's intended to give you a sense for the variety of conditions that affected the material that ultimately went into the planets. So the blue thing here is intended to be the protoplanetary disk, which has a scale height that is a a measure of the distance over which the density changes by a factor of E, falls off, if you will. Scale height increases with distance outwards, so these are always drawn as having these sort of curves to them to represent that. This is not to scale. The protoplanetary disk was maybe 100, 150 astronomical units in size scale. An astronomical unit is the Earth-Sun distance, 149 million kilometers. And the outermost, the giant planets, is at 30 astronomical units, but there is more material beyond that. So this is maybe a generous number. The entire collapsing molecular cloud clump during the collapse itself affected the environment over a size scale of many thousands or tens of thousands of astronomical units, in which the number density of the gas varied from 10 to the 4 per cubic centimeter to 10 to the 8 per cubic centimeter. The density of the air in this room is something like a few times 10 to the 19 per cubic centimeter, so this is extremely rarefied. And in the outermost portion, chemistry associated with ultraviolet light and charged particles coming from stars made that chemistry very, very active, so-called ion molecule chemistry, atomic chemistry. As you move further and further in, the densities go up, and so does the temperature. The temperature in the surrounding molecular cloud is 10 degrees Kelvin. Other than the disk itself, which could have had close to the star temperatures above the vaporization point of the most refractory rocks, aluminum silicates, for example, the rest of the cloud perhaps got up to temperatures of 300 Kelvin in what's called the hot core, and that's enough to vaporize all of the ice grains that might have been pre-existing in this region, which is collapsing to form this protoplanetary disk. So the point of this is to show that ice, such as water ice or carbon monoxide ice, could condense, evaporate, undergo chemistry many, many times during the process of the collapse to the protoplanetary disk. And I'll talk more about the chemistry in the disk in a couple of minutes. Let me talk a little bit about the Kuiper belt. The Kuiper belt is the region where material left over from giant planet formation resides today. So this is a little chart attempting to depict, not very accurately, but fairly well, where some of the small bodies are in the solar system today. There are the planets Jupiter, Saturn, Uranus, and Neptune. The gray is the asteroid belt. And the Kuiper belt is this material that's out here, and it's divided into different dynamical classes, which I'm not going to go through for this purpose, but I'll talk a little bit about in the next slide. The disk itself consists of material that probably formed beyond the giant planets, intermixed with material that was scattered mostly from the Uranus-Neptune region into the disk. That's sometimes referred to as the scattered disk. And material that is being gravitationally perturbed today and is coming into the realm of the planets and can be observed from the Earth. Because the amount of material, the number of bodies increases as the size decreases, what we see are the smallest objects, which are the comets. And it's thought that the Jupiter family comets, which are the ones with periods of 20 years or less, may in fact have originated in the Kuiper belt, either formed in place beyond Neptune or been scattered out there from the Uranus-Neptune region. And that makes them interesting because they could be representative of the material that came into Uranus during its formation. So the Oort cloud, I can see what happened. This is sort of expanded. This should be the Oort cloud. The Oort cloud is material that is at a much larger distance, 1,000 AU out to 100,000 astronomical units. It forms a cloud rather than a disk, and it's material that almost certainly was scattered outward by Jupiter and Saturn, which have much stronger gravity fields. There's a very nice story that seems to fit very well with some observations about bodies in the Kuiper belt. Many of the objects in the Kuiper belt are in a resonance with the planet Neptune. That is, the periods of their orbits are simple integer multiples of the orbit of Neptune itself. So for example, 3 to 2 would mean that Neptune would go around 3 times for every 2 times that one of these bodies goes around. And why they're organized in this way seems to indicate that there is a substantial interaction between those bodies and the giant planets early on. In particular, that these bodies were scattered, began to be scattered by the giant planets, including Uranus and Neptune. And there was so much of this material that that scattering process affected the orbits of the giant planets themselves. It caused those orbits to spread out. Jupiter moved inward a little bit. It's very massive, so it doesn't move very much. Uranus and Neptune are much less massive. They moved outward. The whole system relaxed. And that seems to explain the existence of many of these bodies being in these resonances. The consequence of that, though, is that you can actually calculate, because you can write an invariant that has to do with the inclination and eccentricities of these bodies trapped today, that allows you to calculate where Neptune was at the start of the scattering and how much material was actually scattered out of the giant planet, the Uranus-Neptune region, and the classical Kuiper belt. And the answer is that Neptune was at 18 AU, and something between 10 and 50 Earth masses of small bodies were cleared out. That is, the populations of minor planets were decimated. So if this story is correct, and there's a beautiful review of this by Renu Malhotra in a journal that none of us actually read called Geoscience Letters, and so I recommend it. If this is right, then what is remaining in the Kuiper belt and the comets that we observe coming from the Kuiper belt, the Jupiter family comets, are a tiny fraction of what was there before, because what's in the Kuiper belt today is less than Earth mass of material. And that's dangerous, because if we want to try to associate the composition of those small bodies with what was accreted into Uranus and Neptune, we're looking at the very tail of a much larger amount of material, and we could be seeing material that's not actually typical of what Uranus and Neptune engorged or took in as they grew. Okay, I'm going to talk about solar abundance just very, very quickly. These are abundances in the sun. All you need to know really is that the oxygen to molecular hydrogen ratio by number is about 10 to the minus 3 in solar abundance. The C to O ratio is about 1/2, and nitrogen is only 1/10 the abundance of water. Those are the only numbers you need to keep in mind. Now, what motivates the idea that comets are the objects that most closely resemble solar composition comes from observations of the most volatile materials. So we're not talking here about what geologists would think of as volatiles, like potassium, for example. We're talking about things like carbon and oxygen in the form of water and CO, neon, things like that, things that like to form a gas, because those are thought to be in the ices. So if you plot the relative abundances, these are normalized to silicon versus the hydrogen to silicon ratio, here's the result for the sun, oxygen, carbon, and nitrogen. Comets are just about the same ratio, with nitrogen somewhat depleted, however. Meteorites are not quite as good. They're down by a factor of several. And then, of course, the terrestrial planets have a very different distribution of these elements. So from observations like this, which for all comets except for Comet Halley and Comet 67P, which had mass spectrometer data taken, so direct sampling of their COMI, it appears that comets most closely resemble solar composition. That does not mean that they're representative of the bulk of the mass of material that was in the outer solar system at the time Uranus and Neptune formed. And I'll talk at the end about evidence from the D to H ratio that in fact they were not. So now let me talk a little bit about processes. What processes brought material together and modified it? I've talked already about the complexity of the protoplanetary disk or solar nebula. Over time, this protoplanetary disk evolves by dissipation, either viscous dissipation, as the gas itself, which is in Keplerian orbit, becomes turbulent, and so gases of different Keplerian velocities begin to interact with each other radially across the disk, or by magnetic fields, or gravitational processes, or all three. The disk then is hot on the inside, cold on the outside because of this dissipation. And as it gradually cools, as accretion slows, ices of varying volatility condense at places that are called snow lines. They can also be trapped in trapping of more volatile species can occur within water ice or possibly silicates as well. So a very complicated transition from chemistry to condensation. There's another effect, two other complicating effects are that solids that form in the protoplanetary disk, when they get to millimeter or centimeter in size, decouple partially from the gas because the gas is pressure supported and not in Keplerian rotation, not exactly in Keplerian rotation. So the particles feel a drag force and they move radially inward until they get to a much larger size. So they can separate from the region where they actually condensed out. So let me show a picture of this. This is an old view, a sort of a cross-section of the solar nebula. I want to show it for just a couple of reasons. One is material is always falling in during the evolution of the disk from the molecular clouds, so there's some contribution over time from relatively unprocessed material. At the same time, in the inner part of the disk, the chemically active zone, where temperatures are high enough that chemical reactions reach equilibrium, the molecular identities of the various elements, CO versus methane, for example, nitrogen, N2 versus ammonia, are being completely reshuffled. And that's important in understanding the nature of the material that goes into Uranus and Neptune. And I want to talk about that next. So the chemically active zone in terms of gas phase chemistry is defined as the region close enough to the center of the protoplanetary disk that the rate at which chemical reactions drive toward equilibrium is faster than the rate at which material is removed by turbulence or other processes from that region. So inside that region, predominantly, if we think now just about carbon and nitrogen, because there's no time for any of the others, the exchange between oxidized species and reduced species in this hydrogen-rich gas, because this disk is solar composition, so it's mostly molecular hydrogen and helium, can be summarized by this summary, which is not a chemical reaction. It's just a simple balance. There's a whole network of reactions that go into this conversion from CO to CH4 and water and N2 to NH3. And if you make a map of the regions where in temperature, pressure, space, you get the reduced versus the oxidized species, as John Lewis and Ron Prinn and Bruce Fegley did many decades ago, you get a picture like this. This is temperature versus log of total pressure. This is now the hydrogen pressure. So the carbon and the nitrogen and so on are assumed to be in solar abundance. And at high temperature or low pressure, the reactions are driven to the left, to the oxidized side. At high pressure or low temperature, the reactions are driven to the reduced side. So if everything were in equilibrium, you would expect in the outer solar system at temperatures down below some hundreds of Kelvin that methane would dominate. But methane doesn't dominate because the reactions are so slow below about 1,000 Kelvin, or if you have some catalyst like iron sulfide, below 700 Kelvin, that for a temperature pressure profile in the solar nebula, such as is shown here, you always get carbon monoxide dominating in the chemically active zone, and that is quenched in below 1,000 or 700 Kelvin. So CO is the dominant carbon-bearing species, and a little bit less definitively, N2 is the dominant nitrogen-bearing species for the same reason. So these lines are where CO equals CH4 in equilibrium and N2 equals NH3. Now notice if there's subnebulae, higher density regions around the giant planets themselves, those could in fact have methane and ammonia dominating over CO and N2, but I'm not going to talk about that. The result of the fact that CO and even CO2 dominate in the protoplanetary disk means that any solids condensed in that disk are very sensitive to the carbon-oxygen ratio because CO, carbon monoxide, is carbon and oxygen. And so whatever oxygen ends up with the carbon, plus what goes into the rock, because there's a lot of oxygen in rock, only the rest is left over for water. So for a solar C to O ratio, if the nebula were dominated by methane, you'd have plenty of water ice, and then the green is intended to represent methane and other carbon-bearing species. But in a CO-dominated disk, as we think is the case, ice is only 2/3 the abundance that it was in the reduced case. And if something were to occur that would raise the carbon to oxygen ratio in regions in the disk up to 0.8, you would have almost no water ice at all. Now, the density of planetesimals that one gets from a solar C to O ratio and a highly oxidized nebula where CO dominates corresponds very well to the density of Pluto and Triton, and also, as far as anyone can tell, the ice-to-rock ratio in comets. So that appears to have obtained. But condensation can affect the C to O ratio, and I'll get to that in the next slide. Condensation in the disk occurs where, if we consider a particular species, like ammonia, for example, or water, the partial pressure of that species at a given temperature exceeds the saturation vapor pressure at that temperature, at that point in the disk. Condensation should occur. And this is just a plot of where, for a pressure-temperature line in the protoplanetary disk, where in temperature and pressure space, these various species condense out. Now, it's possible that this is the way things worked in the outer solar system, that every individual species condensed out and it's had its own ice line or snow line. But it's more likely, perhaps, that especially some of the more volatile species down here, before they had a chance to condense out as ices, were trapped in water ice, trapped either in a glassy or amorphous form of water ice, which adsorbs very effectively, or even in a volumetric trapping process called clathration, where the water ice changes form and traps species in cages within the ice. Kinetically, this may not be something very favorable in the disk, but it has been considered as a possible way of trapping volatiles. If things are trapped in clathrate hydrate, the composition of the volatiles trapped in the ice is not the same as the composition in the gas that is in solar abundance. An example of this from a very old paper by Dave Stevenson and myself in 1985 is the ratio of the noble gases to each other. Solar here is given by this dashed line as a function of the temperature of trapping, and it really can be very, very different from solar. So the problem here is there are many processes that affect these abundances, and just measuring a given set of properties like noble gases and so forth is not going to get you the whole answer, but it'll get you part of the way. Now, let me say one other thing about snow lines, and then I think I have 10 minutes left after that. Is that right?
Yes.
Okay. So the other thing about snow lines is that they locally affect the carbon to oxygen ratio, and they can do this in simple ways and complex ways. So the simple way, as shown here in Oberg et al., is a plot of the carbon-to-oxygen ratio versus heliocentric distance. When you reach one of these condensation fronts in the disk, the assumption here is that water, CO2, and CO all have condensation fronts. They all condense as their pure ices. And then very simply, you can do a mass balance and say whatever is not in the gas phase is now in the grains. And so in the gas, the C to O ratio increases because water condenses first and takes out oxygen. And then in the grains, they progressively are depleted until you get to the CO2 and the CO fronts here where their carbon abundance goes up again, simply because you're partitioning the carbon and the oxygen between the gas and the ice. But there's a more subtle effect. If you actually track the formation of snow lines in a model of the evolving protoplanetary disk, snow lines can become very complicated. Ice that forms will bunch up, but it will also drift inward as it reaches this centimeter size scale where decoupling occurs. But the vapor will then diffuse like a cold finger effect through that condensation front, and it will dry out the region just inward of the condensation front. The drifting pebbles will begin to sublimate, and they will add more gas to that region, but their sublimation is actually rather slow, and they can potentially move a significant distance away from the snow line before they actually do sublimate. And if you include all these effects, as Ollie Dibb and colleagues did in 2014, you can get some very weird carbon to oxygen ratios in the gas phase in the disk. This is an example at 2 astronomical units, the C to O ratio versus time. There's a water snow line in this model. There's a CO snow line farther out. And the C to O ratio can go from solar, actually he has solar as a half. I put a line here, but that doesn't matter, up to C to O of almost 1, and then it can go down again as these snow lines evolve. So that, it's like fractional crystallization in a magma chamber. If you crystallize material from a melt and it falls out, the composition of the remaining melt is different, and so you will then get different materials, different solids crystallizing from that evolved melt. This is sort of the same thing. Okay.
10 minutes?
10 minutes. So what markers exist today to identify reservoirs and processes? So clearly we want to measure as many of these elements that are represented in the solar nebula in various forms. CO, CH4 are carbon, nitrogen, NH3 are nitrogen. The noble gases are important because they don't form molecules, so their identity is not altered through the formation of molecules. And we have such a record for Jupiter. This is the mass, the abundance relative to the sun, where the sun is 1, for these different elements. In these giant planets, carbon is mainly methane, nitrogen is mainly NH3, but that's because of processing in their envelopes themselves. They could have fallen in as carbon monoxide trapped in water ice, or carbon monoxide ice, or N2 trapped as well, and then the high temperatures and hydrogen pressures in Jupiter and Saturn at least, will convert those to methane and ammonia. The Jupiter story is a little bit complicated, but I want to move quickly to Uranus and Neptune. They have a much higher enrichment of carbon by orders of magnitude than does Jupiter. Jupiter is a factor of 3 or 4 relative to solar. These are factors of 40, so it's an order of magnitude larger. The nitrogen abundance in Uranus, surprisingly, seems to be very, very low. The microwave emission from Uranus is such that there doesn't seem to be much ammonia. So is that a depletion due to some phase transition inside of Uranus? I think we'll hear about that perhaps in Krista's talk. Or is it primordial? Was nitrogen lacking from the disk? Now, I would point out that when we look at Jupiter, just very quickly, the noble gas distribution for argon, krypton, and xenon is almost uniform, but for comets, 67P, it is not uniform. So in this respect, comets don't seem to be a very good representative of the material that enriched Jupiter, at least, with noble gases. Is it for Saturn, Uranus, and Neptune? We don't know, because you cannot measure those noble gases without going in with an atmospheric probe, and only Jupiter has been studied with an atmospheric probe. That's Galileo. So I want to finish in the last 5 minutes by suggesting another reason why comets might not be the best model for the material that enriched Uranus and Neptune in heavy elements. This is the deuterium to hydrogen ratio. So the deuterium to hydrogen ratio in Jupiter and Saturn is low. It's thought to be what it was in the original protoplanetary disk. The comets, it's high and rather uniform. Ignore the ones on the white part here because we want to focus on D to H in water, which is what's measured in comets. This is D to H down here in molecular hydrogen. And for Uranus and Neptune, the numbers measured a few years ago by the Herschel infrared satellite are a factor of about 2 or so enriched over Jupiter and Saturn. That is a peculiar number because if you think about the way to create that enrichment, you would imagine that ices with a deuterium to hydrogen ratio like that in comets, if you think comets are in fact representative of the stuff that enriched Uranus and Neptune, that material came in, it mixed and re-equilibrated with the hydrogen that was in Uranus and Neptune, and the result is this elevated value that you see today in the HD in Uranus and Neptune. But that is not actually what you get if you do that calculation. So this was first done back in 2013. It is a simple mass balance with some important assumptions that the D to H equilibration between water and hydrogen is what is obtained at high temperature, where there's no fractionation that occurs, just re-equilibration, that there's full mixing, and then use interior models to determine the amount of hydrogen relative to ice. For this calculation, the deuterium in the silicates was not considered, and I'll get back to that in a second. But what you find if you use the D to H ratio from Herschel for Uranus and the cometary D to H ratio, and you assume that the protosolar gas is the value we see in Jupiter, what you get is that only between 15 and 30% of the non-hydrogen helium part of Uranus can be ices. The rest has to be rock. So if you believe this, Uranus and Neptune are not ice giants, they're rock giants, which may not affect our ability to sell the mission, but that's just the way it is. However, there are a lot of caveats to this calculation. For one thing, the idea, some of these are cut off, but let me just tell you what they are. I mean, Uranus may not be fully mixed, number one. The re-equilibration may not have been complete. This calculation ignored D to H in the silicates, and the silicates coming into Uranus and Neptune could have been hydrated, which means they would have had water, which means they would have had deuterium in them. The D to H ratio in the water of hydration in carbonaceous meteorites is a factor of a few lower than what it is in comets, and that would give you a sensible result. So, you know, it's either that it is a mostly rocky composition, which would be consistent with the D to H ratio in the rocks themselves, or the calculation is simply oversimplified and Uranus is not well mixed. Now, one model that, so I didn't explain that very clearly. Let me step back and say it again. Even though you ignore the rock part, the D to H ratio in the rock, that is overwhelmed if you assume that ice is the dominant non-hydrogen helium material that went into Uranus and Neptune. So this calculation, if the assumptions of mixing and re-equilibration are right, would still tell you, even if you included the rock component, which has a lower D to H ratio, it would still tell you that Uranus is not mostly ice-rich, that it's mostly rocky. But we can perhaps untangle this by looking at noble gases, because noble gases are also partly trapped in rock. The carbonaceous chondrites have a noble gas pattern, a particular noble gas pattern. The comets have a particular noble gas pattern, as you saw as well. And so again, being able to measure that in the interior, in the atmospheres of Uranus and Neptune is going to be very important. There's one model that was published by Ali Dib and colleagues in which they argued that one way to get a mostly rocky composition, to get rid of the ice, would be to condense all of that material that goes into Uranus and Neptune just at the carbon monoxide snow line. You get much less water, you have an elevated C to O ratio there. You would get very little nitrogen because nitrogen is depleted from its snow line farther out. And so you would predict a particular carbon to nitrogen abundance that looks like what we see today in Uranus, where you have a high carbon and a low nitrogen. But again, 2 minutes, got it. But again, the ammonia could possibly be simply dissolved out in the deep interior, which we'll hear about later. So, and then the other possibility, which is the obvious one, going back to this, is that comets and their D to H ratio are not a good example of the bulk amount of planetesimals that went into Uranus and Neptune. The Uranus and Neptune did acquire icy planetesimals, but their composition is different from comets. So here is one way to look at this. You can imagine the elements. You can imagine different models, some of which I've talked about for the composition of the material that went into Uranus and Neptune. You can measure these potentially with the mass spectrometer on a probe. There are some diagnostics here. I didn't talk about all the models on here, including photoevaporation, but there is potentially some hope that one could untangle these possible models, except that for even dramatic differences like this, you don't know if the difference is primordial or due to phase separation inside of Uranus and Neptune. So let me close then with my conclusions. We really know very little about the actual source region of Uranus and of Neptune, because even though we have samples of comets and good samples from the, particularly from the Rosetta mission, that material is the tail end of a distribution of upwards of 50 Earth masses, the vast majority of which is gone. It's not even accessible to us. It's not in the Oort cloud. It's not anywhere that we know of. So Uranus and Neptune could have formed from CO-rich water-poor solids, could have formed from ice-rich solids with a different composition, including a different D to H ratio than comets, or it could be something else. But that would point to comets being a poor match for the heavy element abundance. So to untangle this, getting noble gases is important. Getting as precise a value as possible for the atmospheric helium abundance is important, because any model in which CO ice dominates, the oxygen would react with the hydrogen inside of Uranus, use up much of the hydrogen, and then helium would be elevated above the solar value. And combining that with gravity mapping that could determine how much rock versus ice, and all these things could be done by a Uranus orbiter probe. It's important, I'll mention before I get chased off the stage, the behavior of water and other materials at the pressures and temperatures in Uranus are really not well understood. Could nitrogen be dissolved as ammonia in a deep ocean on Uranus? Could it be, as suggested by Shi et al., that there's a helium-ammonia stable phase in Uranus at a megabar? All these things are questions that we hopefully will talk about during the week, but this is at least a slice of the state of knowledge as we understand it of the source materials. Thank you.